All right, so thank you. Good morning. I'm Erik Thostenson. I'm faculty in mechanical engineering and materials science at the University of Delaware. And for many years, I've been affiliated with the university's Center for Composite Materials. And we're celebrating our 50th anniversary coming up. And over about the past 20 years, I've been involved with ongoing integrated research in processing, characterization, and modeling of carbon-based nanostructured composites, both carbon nanotubes and graphene, and also combining reinforcement scales. So what I'd like to, first start off with today is this is some work that I did 20 years ago. I was among the first to grow carbon nanotubes directly onto carbon fibers, and that's what you see here. And I think as an engineer, what always intrigued me actually and drew me to study composites is that we design them at varying lengths of scale. We don't take material properties just as a given, but we design the microstructure and to get ultimately our final properties. So this is what you see here. What you see here is in the middle, that's a single carbon fiber that is about 7 microns in diameter, where we've grown carbon nanotubes on the surface. And what I like to call this is a multi-scale hybrid composite, because we don't just are combining different types of reinforcements, but we're combining different reinforcement scales, scales that are 3 orders of magnitude, even smaller. So today, really what I want to do is I want to highlight a manufacturing process that we've been studying for about the past 10 years, which has really been an enabling technology for some multidisciplinary collaborations, specifically utilizing networks of carbon nanotubes for sensing. So as an engineer, my background was in traditional fiber composites before I started working in nanomaterials. And so I pulled the quote on the left from this interagency working document. And it seems, this nanotechnology, we're going to build everything from the bottom up. But this is something that has been done in composites for years, is that we really are bottom-up design. So we select the constituent materials, we tailor their interaction through the fiber matrix interface or interphase. We bend and twist fibers together and laminate them all the way up to the net-shaped composite. And of course, I flew over here on a composite plane. So it really is, it's something that has been done in composites for decades. So this bottom-up manufacturing was nothing new to me. But really one of the unique things that we discovered was this ability of the carbon nanotubes and other nanocarbon to create conductive networks. And I realized that we could utilize that as a sensor, is that the conductivity, you can think of these nanocomposites as discontinuous wires, and the conductivity is dominated not by the conductivity of the reinforcement, but the contact resistance, or what we call quantum tunneling between there. So there's a lot of things that occur at that interface, but particularly from a mechanical point of view, we can look at if we're straining it, it's what we call piezoresistive, is that the resistance changes much more than we would expect simply based on a strain and a Poisson contraction, because you have hundreds and thousands of these tunneling gaps. And then really where the value added is detecting cracks. So we were able to create conductive networks within the fiber composite to detect microcracking, and that was some of our first work. And so this is a crack in a composite, and what you can see is in that very small crack, which is only about a micron, you can see the nanoscale reinforcement protruding into that crack. And I think when we first published this work, it drew a lot of attention because it's a very practical application of nanotechnology. In order to sense a microscale crack, you need a nanoscale wire. So it drew a lot of attention all over the world. And we've done quite a bit of work. This was maybe almost 15 years ago now. but we've done a lot of work over the years. And what I want to do is today I'll highlight some of the interdisciplinary collaboration over the last couple of years for structural monitoring, utilizing this material for structural health monitoring. And then most recently, an exciting area is utilizing this to detect human motion. So from structural health monitoring to human health monitoring. So first, I just want to highlight some of our work because really this is, it's fundamental from the characterization and the manufacturing point of view. It's really been the enabling technology. So I'll very briefly highlight this issue of electrophoretic deposition. What we were first doing is looking at growing the nanotubes directly using chemical vapor deposition. But this is a very energy-intensive process. It only works on a few fibers, in particular high-temperature fibers. And while it's somewhat scalable, I didn't really see it as something that was going to make a big impact. So my interest was, well, can we do this? Can we combine these reinforcement scales using a different technique? So again, this is pretty high temperature process. We're well over 600 degrees. For many reinforcements, and certainly any polymer material, we would be actively degrading it. So what I started looking at was utilizing electrophoretic deposition. So what we do is we create a dispersion of nanoparticles, in this case carbon nanotubes. We disperse them in water. And we chemically functionalize them, in this case, with a cationic polymer. And when we lower the pH, they protonate. And that does a couple of things. The positive charge stabilizes the dispersion. So the positive charge will repel each other, but that gives it mobility. So what we can do is we can use that electric field to deposit the carbon nanotubes. So what you see on the right-hand side is where we've cross-sectioned a fiber, and what you see on the very top of the fiber and surrounding the fiber is almost kind of a sponge-like coating, and that is the carbon nanotubes that are functionalized. And those carbon nanotubes bond to the surface of the fiber, and they also bond to each other. So they're fully integrated. So this is just, I think in our case, we can control the process. We have a lot of control over the purity and functionality. And really, it's that surface charge, which not only enables the process, but those chemical functional groups bond to the surface of the fiber. And I think our original interest was in modifying the fiber matrix interface in traditional composites. So what we have, really what you see here, this is just a cartoon of the, a cartoon of the, on the right-hand side, a cartoon of the carbon nanotubes and the chemical functionality. Again, in the upper left-hand corner, what you see is a scanning gallium ion image. The bright areas are the regions where the carbon nanotubes are. So that shows up as bright, and you can see that we're integrating those into the fiber bundles. And again, on the bottom, what you see is that porous nanocomposite coating. And certainly, it has unique mechanical properties as well as electrical properties. This is just some nanoscale characterization. On the left-hand side, just bulk epoxy, and then also our nanocomposite, relatively high fiber volume, nanotube volume fraction. And you can see the indents are much shallower. So we're stiffening it. And on the right-hand side, you also see that there's increased toughness, and that's a nano scratch test. So those vertical lines that you see, and you see that debris, and if we move in closer, you'll see a lot of pullout. We can also control this process quite a bit. We can control the coating thickness. So on the left-hand side, you see a coating which is in the few hundred nanometer range, and on the right-hand side, less than 100 nanometers. So again, you see that porous type of a coating. And then also, I could spend an hour talking about this, but we have a good understanding on how we can control the location on the top. What you see is basically a coating All the fibers are uniformly coating. You see the bright rings. We can tailor the interface, the interlaminar regions, and then also using other techniques, we can force more and more nanoscale reinforcement into the fiber bundle. But one of the unique things is that it's fiber agnostic. We can coat anything. In fact, we can coat, we developed the chemistry to bond to carbon and glass and aramid type fibers, but the traditional fibers, the surface treatments are quite compatible. So we are able to bond to natural and synthetic fibers, and certainly any of these fibers would quickly degrade if we were trying to grow CVD. And it's something that's scalable. And we've developed a scalable process roll to roll. This is actually will be published in Composite Science and Technology. And we built a small pilot line so that instead of making a few square inches of material, we can make feet. So in this last part of the talk, I'd like to spend this time to say, well, we developed this processing technique. What do we do with it? And this has really opened a new door for me. I'm a materials scientist by trade, more on the mechanics side and mechanical engineering. But I've been able to collaborate with some of my colleagues in civil engineering and also now biomedical engineering and utilizing these sensors in novel applications. And one of the things that we talk about is 20 years from fundamental research to commercialization. I think we're right on the edge of being able to do something interesting for commercialization. In fact, one of my students and I created a startup company. So the first thing I just want to mention is that, where we were looking at damage sensing, we were very successful at determining that there is damage. Most recently, maybe about 7 years ago, we started looking at, well, where can we localize that damage? So what you see here on the left and right, those are where we're doing impedance tomography. So we're measuring conductivity around the boundary. And we solve the inverse problem using finite elements to get the conductivity distribution. And most recently, we're utilizing that for novel pressure sensors, what you see on the right. And then also flow and cure in composites manufacturing. So these have it's really a multifunctional sensor where we can utilize it for a variety of applications from manufacturing, sensing, and then also damage sensing. And I guess in the first one, so I showed this is crack growth and branching where we're looking at impedance tomography. And our interest in this project was looking at structural health monitoring for rehabilitation of civil infrastructure. And it's certainly in the USA, that's certainly a critical area, is that a lot of the infrastructure is aging. So again, because we can scale this process, this is a concrete beam. I won't talk too much about this, but that beam is 4 meters long. And it has shear U-wraps on it and also integrated sensors. And one of the biggest issues is fatigue damage in civil infrastructure. On the right-hand side, that's actually a bridge that in Delaware that we went out and we did some monitoring on. And what you can see, there's holes drilled, and that's the traditional way of trying to repair a crack, is that you drill a crack stop hole to blunt that the stress concentration at the tip. So our idea, and we're talking to our civil engineering colleagues, they really like composites, but critical barrier is that you're covering up the crack, so they can't inspect it anymore. So our idea was, well, hey, we have these cool sensors, let's see what we can do. We looked, it really took this was funded by the Federal Highway Administration, a 5-year program. We took it from idea to actually putting it on a bridge. And so what you see here, these are some of the specimen configurations that we tested in the lab, just the baseline where we drill a crack stop hole, but where we also apply a composite repair with and without a crack stop hole. So this is actually the specimen that you saw in the previous picture, is that where the sensor is a compact tension specimen. Although it's not very compact, it's quite large. And what you can see on the response is the sensor response so that we can detect that load. But most importantly, we can detect the crack extension. And so we've done that in the lab. So we've done both modeling. What you see on the bottom is some finite element modeling, as well as digital image correlation to track the motion of that crack. We also have a sensor on the other side. So this is a simulation where that crack is growing, and what you see is that as the crack gets longer, that stress intensity at the crack tip increases. So this next slide, the first one shows this axial stress in the composite. Well, as that crack grows, the composite starts to carry load. But of course, you can't see it. And on the right-hand side, the interesting thing is that actually as that crack grows and the composite carries more load, that stress intensity decreases. And we've done quite a bit of work, both fructography, looking at the crack position, and also we can measure what's called the back phase strain. And as what you see in the videos on the backside of the specimen is in compression, so we have a strain gauge right in that area, and we're able to track that back phase strain. And where you see it start to deviate, we actually fatigue the strain gauge. So, but we're able to track the motion of that crack and the length of that crack very accurately, not only using the back phase strain gauge, but also looking at the fracture surface. And we actually put it on a bridge. So this is a bridge that's downtown Wilmington, Delaware. We have a sensor in Portland, Oregon, and also a sensor on another location in Texas. So this is the bridge. It's a drawbridge, actually. In the background, you see the Joe Biden Jr. train station, the red building there, downtown Wilmington, Delaware. And the first day, we were kicked off the bridge by the tall ship. So delayed us a little bit. But those are the sensors that were applied. Those are sensors that are bonded onto a structural composite and then installed on an active fatigue crack on the bridge. And as a repair, and we added our sensor. On the right-hand side, we have it connected to the cellular network, so we're feeding that data live. You can look at it on your phone. So that data acquisition in a solar panel is very small, and it's just hanging off the side of the bridge. But this is a unique sensor in terms of, we could actively monitor it. It could be utilized as inspection. We can use it with or without a composite repair. And we validated that all in the laboratory. So this last part that I want to spend about the last 10 minutes talking about is an exciting area that we've moved into, in particular, utilizing these sensors and taking them in a new direction. Previously, almost all of our sensing was done where you embed the sensor in a composite or disperse the nanomaterial in the polymer matrix. But in this case, what we're doing is because the coating is actually very soft, even though the nanotubes are quite rigid, it's almost like a sponge. So it's soft to the touch, but it's bonded, very well bonded to the surface of the fiber through the chemistry. And so we were able to coat a wide range of materials, and we developed some unique sensors. So this is, on the left-hand side, you can see in my hand, there's a pressure sensor that we developed that's coated. It's a non-woven aramid fabric coating. And there we have it laminated in a plastic sheet. It's very thin and flexible. You can put it in the sole of your shoe. And on the right-hand side, that's one of the students who was working in the lab testing it out in the graduate student office. And this is a unique sensor because it has an extraordinarily large dynamic sensing range. So it's a non-woven veil that's coated. And so it's sensitive to finger pressure, just very, very light touch. It's sensitive, of course, to body weight, what you saw in the video. And then we took it into the manufacturing lab and drove over it with the forklift. So literally from touch to tons. And it's a nonlinear response, but it's actually The mechanism is quite interesting, and I won't go into this too much, but it's that sponge-like coating is that the fibers contact each other, and then you eventually compress that coating. And what you see here is the junctions of the coated fibers and that non-woven material, and it's at those junctions where we get that sensing response. So it's a very unique type of sensor. It's thin and flexible. That's a cross-section of the aramid fiber, and you can see we've deformed it a little bit, and the coating is still well adhered. So the idea for kind of moving into biomedical applications grew out of, I actually read an article in the Philadelphia Inquirer newspaper that was actually some research from my colleague who was just down the hall. And what they were doing is that they were making a walking boot, which would provide feedback if you have a lower leg injury, such as a broken leg or perhaps a knee replacement. From a clinical point of view, what they were interested in is that, well, it's good to put some weight on it because that helps healing, but you don't want to put too much weight. And the current, because that could re-injure that limb. And the current way they do is they have you go into the doctor's office and stand on a bathroom scale. And then they should stop when you hit that level. Well, this article talked mostly about all the trouble they were having with the sensors, and they had to redesign the boot. And I said, hey, we need to talk to Jill because we have the perfect sensor. And in fact, the current incarnation of the Smart Boot has our thin film sensor in it. And I consider it, it's like a quantitative Fitbit, is that it doesn't tell you just how many steps you've taken, but also what force range you were in. So at the end of the day, you could say, oh, 60% I was in the right force range, 20% I was too high, 20% I was too low. So that would provide not only active feedback, red and green, or haptic feedback immediately, but also be a record of where you are. So we did this, and we were funded by NIH. We validated this in the laboratory. We're using very inexpensive data acquisition. On the left-hand side, that's the PhD student who was working on the project, Sagar, and he is walking on an instrumented treadmill in the physical therapy biomechanics laboratory. And so it's a treadmill that has a force plate integrated. Also around, there's full motion capture. But of course, you can only do this in a laboratory. But we validated these sensors. We tested on a wide range of human subjects, and it's quite accurate. And I think one of the things you notice is that it seems that the sensor drops a little bit when you're going fast. We're just not taking data fast enough, so that sometimes we miss that peak. Okay, so on the left-hand side, basically we have a sensor in the ball and the heel of the foot. That black line that you see on the right part is actually the data from the treadmill. So we're getting very accurate data from this novel sensor. Whoop. And also now we can walk over different terrain, not just on a treadmill. We can go out, walk up and down stairs, walk on carpet, walk on grass, and what you see is walking upstairs and those different forces that are acting on the foot. And my colleague's research, she is specifically looks at stroke rehabilitation. So our interest was also looking at joint rotation. So we developed a unique sensor. What you see on the right is one of the students moving their elbow. And one of the things we thought it could be used in virtual rehabilitation. During COVID, one of the things that happened was everything went online, Zoom meetings and also Zoom physical therapy, but it's difficult to detect range of motion through a Zoom call. And when we designed this sensor, it's extraordinarily sensitive. On the left-hand side is graph 3,000% change in electrical resistance. Extremely sensitive. In fact, I told the student, I'm like, are you sure you didn't multiply it by 100 twice? And then, of course, we can put that also on the knee sleeve. And the knee sleeve, so we have our human subject standing and sitting. again, very similar response. So, and because it's soft to the touch, it's breathable. The only thing, you wouldn't even know what the sensor, that you were wearing the sensor. And of course, you can have it in any color as long as it's black because it's carbon, right? Okay, so, and of course, actually, we've spent a lot of time understanding the fundamentals and the mechanism, and actually the biaxial stretch is one of the key things. But it's so sensitive, so you can utilize it on, to not only gross motion, but very delicate motion. On the left-hand side, we're gripping different diameter objects, and again, you see very large change. So it can be utilized for both the large-scale motion, but also delicate motion. On the right-hand side, the video, you see that the clenching the fists and just that motion of the muscle contraction is resulting in a significant sensor response. So we recently received funding, additional funding, to look more into the garment-based sensor. We've already validated the force sensor. On the left-hand side, that could be a paradigm shift in monitoring rehabilitation. On the left-hand side, that is actually a photo from the biomechanics lab of some subject, all instrumented up. On the right-hand side is our elbow sensor, and we've miniaturized the electronics just using off-the-shelf type of things that can easily be worn, and it has a Bluetooth shield so that it can send it to your phone. So this was just kind of a fun part, is that we were looking to validate the sensors, and we actually 3D printed the hand to detect, to validate it, because everyone has a different size hand. So we wanted to have something that was repeatable, but the student flipped it around, and he then could put the sleeves on his fingers and utilize that to control. Okay, so that's really what I wanted to cover today. So just a few brief conclusions in the last couple of minutes that we have. So really, it's a scalable manufacturing that we developed. This electrophoretic deposition process is really what's the enabling technology. It's scalable. We do it at ambient temperatures. We use water as a solvent. And we can utilize this real-time monitoring, can be a quantitative measure of damage in a composite, but also we can modify, because these have tremendous application flexibility, we can modify this sensor for a variety of applications. And that's where I mentioned, I work with my civil engineering colleagues, work with my biomedical engineering colleagues. Been a lot of fun for me, actually. And we get funding too, right? So these fabric-based sensors show remarkable sensitivity, both in the dynamic sensing range and also the what we would call the gauge factor, or the sensor sensitivity. And so we've validated, we've shown that we can use it for both structural health and human health. Okay, so with that, I just want to make a couple of acknowledgments. Of course, all the students and postdocs, people who are actually doing the work. My collaborators, Thomas and Jennifer in civil engineering, Jill in biomechanics, and as well as some colleagues in electrical engineering and computer science, and also Andrew Ryder, who's at DST Group in Australia. So we've been fortunate to have a wide range of funding, and very recently the NSF funding to do more human subject testing. So just as a kind of a very quick conclusion, where are we? Delaware. University of Delaware, right? And so we're centrally on the East Coast. Our Center for Composite Materials is, as I mentioned, celebrating 50 years. And as part of that 50-year celebration, we're hosting ICCM. It was supposed to be this summer, but delayed due to COVID. First time I visited Korea a number of years ago was for the ICCM conference, so I encourage all of you to come to Baltimore in 2 years. And I guess with that, I'm happy to take any questions. And I ran out of my business cards on the first day, so feel free to connect with me on LinkedIn. So.
Okay, thank you. It's a very interesting presentation. Anyone from floor, the questions? Please give the mic.
Thank you, Eric, by accepting my invitation to present a very nice talk. I appreciate. And I have a very simple question. First session, you using to modify your carbon fiber by using electropolysis. Did you try to measuring any interfacial decreasing, increasing, or tensile strength increasing due to the stress concentration of the fiber? Is my first question. Second question, I'm using the similar work like you using the resistant mapping by two-dimensional. It's very nice view. I like ask you, did you expand from two-dimensional to three-dimensional electromapping to see as a function of the depth effectiveness? You show me two-dimensional electromap, very nice. Did you try the three-dimensional? Second question. Third question, very nice application for using health monitoring using electrical resistant. Did you try to any adhesive effectiveness long term, like folding, the bending, folding, the adhesive, maybe sensing sensitivity will be decreased due to this adhesive deterioration effectiveness.
Yep.
So please.
So I guess if I can remember, the first question was related to the interface. Right? And we've done extensive interface characterization, both at the laminate level, but also at the micromechanical level. So we've created model interfaces where we actually can control the chemistry of the surface. And so rather than rely on a proprietary sizing, so we ensure that we have chemical bonding, but we've also done things like single fiber test, microdroplet, and also fiber pullout, and everything supports that improved adhesion. And I guess one of the other questions was related to the garment sensor and the durability. And in fact, we bought a small washing machine, and we washed these hundreds of times, and it's very durable. And so there's little degradation. And the second one was related to the fatigue. So it was a compact tension specimen. So that was our work where we validated it in the lab. And actually, I think one of the things that was one of the key parts was that one of the things, and I kind of skipped over that slide, but the addition of the composite resulted in a 400 to 500% increase in the fatigue life. But the durability of the sensor, we've evaluated that in the field, looking at that crack growth, and also could monitor that.
So
that cover it?
Yeah, the conclusion, by the way, is there any comparison between the strain gauge sensor and your electrical resistant sense, economically, practically? I think your electrical resistant health monitoring sensor much more benefit than strain gauge. Strain gauge is expensive.
I'm sorry, I missed part of that.
Strain gauge. Okay, I can talk to you.
So, I mean, I guess it's certainly that we've done quite a bit of, and there, in terms of durability and also thermal characterization. So that's something, hopefully, if I understood, that's something that we're addressing in ongoing work.
Okay. Anyone from the floor? I have questions. Professor, I have a question.
Sure.
This kind of the nanostructures, nanotechnology, because of the development of a manufacturing process, theoretically is a very unique and very uniform properties, reinforcing property we can have. But many cases when we try to make a mass productions, we have some difficulty to make it uniformity or repeatability, consistencies. What do you think to keep that if we have to use that, especially for healthcare sensor? It is very accuracy and consistency is very important, uniformities. So what do you think? Theoretically, it's possible, but You mentioned about functionalities, functionalizing of the nanomaterials, and also secondly, interface addition, and also we can consider about the dispersion technologies.
Yeah.
With your the research, do you think the multi-scale nanostructures manufacturing process, you can keep that uniformity or consistency, especially repeatabilities, how to make it? Which one is better, most concerned, like functionalizing or dispersion technologies of that?
Yeah, so I guess the first thing, it was related to the tubes themselves, I guess, and one of the problems that I've seen, I've been working in nanomaterials for a long time, and we used to grow our own, but one of the problems I see is that there is a large repeatability or large variability in the companies that are making carbon nanotubes. I think it relates to the sensor. So our dispersion technology, I didn't really talk about that, but we do an ozone functionalization to treat the surface of the tubes, and then we graft on polyethylene amine. And it's that amine group that forms specifically for carbon fiber, if you have an oxide surface, that amine group reacts with the surface, but the amine group also reacts with itself. And that's one of the reasons that we have a very strong bond to the surface of the fiber. And then when we wash it or we do interface characterization and things like that, it's quite repeatable. So as it relates to the sensor aspect, the biggest variability in the sensor performance, particularly the garment-based sensor, the biggest variability is not the sensor itself. In fact, we have very good repeatability of the sensor, but it's actually how the person wears it. And in fact, we had another group went in and took the data, and they weren't wearing the sensor at all on their elbow. They were using it, put it on the side of their sleeve. We got a response, but it was completely unexpected. But and in fact, that's why we're doing even the ground reaction. We have calibration protocols set when we do those validation. But even for the pressure, for the foot sensor, which we've done the most characterization on, we do measurements of their foot. And actually, for the validation also we use sandals, and it actually, because you're preloading it, some people tighten the sandal down a lot, some people don't. So that's something that we're looking at in terms of validating those sensors. But we've done repeated over and over, and the sensor-to-sensor repeatability is very uniform. And that's partly because we have such a uniform coating, and we're controlling that chemical functionality. So that tunneling gap is actually very consistent. The other part is that the sensor-to-sensor repeatability, but also the long-term sensing performance. So we've stretched it, thousands of times, and we see the same response. And the same in the pressure sensor. We've done long-term testing of that. But as I mentioned, it's more application specific in terms of the elbow, and that's what we have new funding to pursue. So hopefully, in a couple of years, I'll be able to answer that in much more detail. So.
Okay, thank you very much.